Have you ever noticed when you're driving that anyone who's driving slower than you is an idiot, and anyone driving faster than you is a maniac?
Say, look at this idiot here. Will you just look at this idiot just creeping along? Whoa, look at that maniac go.
I know exactly what George Carlin is talking about. Here's George Carlin in his 1977 Volkswagen Rabbit, chugging along at a modest 60 miles per hour. And I've chosen to label his velocity VGR, which means the velocity of George with respect to the road. Velocity of George with respect to road. We'll be using subscripts in this discussion. So G is for George, R is for road or roadway. And here comes that maniac he's talking about, coming up from behind, and she's hauling at 80 miles per hour. And I've labeled her speed or her velocity VMR for velocity of the maniac with respect to the road. So both of their velocities are referred to the stationary roadway. I could have said velocity with respect to the earth as well, or even the ground, but I decided to use G for George. Imagine now that you're riding along with George and you're completely oblivious that you're actually in a vehicle that's moving over the roadway. Maybe you think that you're just in a car or you're in a room that's not moving. That's why I've removed the roadway here. And try to imagine what things would look like from your perspective. Would you really see this maniac passing you at 80 miles per hour? Forget about what you might know about their actual speed. I'm asking you to imagine what it would look like. How quickly do they appear to be moving? If you're going 60 and they're going 80, I think it's fairly obvious that they would be approaching you at a more modest 20 miles per hour. So you can make the maniac appear to be going slower by being in motion yourself. And you'll notice, of course, that 20 miles per hour is the maniac's actual 80 miles per hour over the roadway minus how fast George Carlin is going. This is, I'm sure, what you did in your head, but we can codify that result in an equation because you'll observe that the equation you've actually used is to say that the velocity of the maniac with respect to George, that's the 20 miles per hour, is her true velocity with respect to the roadway minus George's velocity with respect to the roadway. That's what we've really done. VMR is the maniac's velocity with respect to the road. If you subtract from that George's velocity with respect to the road, then you get their so-called relative velocity. Now we can rewrite this in a slightly different form. George moving over the roadway. Again, pretend that you're in the car. You think you're at rest. You're just in a room that's not moving. If you happen to poke your head out the window, wouldn't you see the roadway going the opposite direction? If the car is actually moving to the right over the roadway, then when you stick your head out, it looks like the roadway is moving past the car to the left, as I've indicated here. So from George's perspective, George Carlin's perspective, the road is moving with respect to George with a velocity of negative 60. Negative because it's in the negative direction. It's going to the left. So this is the velocity of the road with respect to George. See the relation there? VGR is 60, so VRG is negative 60. There's an opposite relationship there. Let me go back to the equation that we just wrote down and make that substitution. Instead of VGR, I'll recognize that George's velocity over the road is the negative of the road's velocity past George. And of course, two minus signs turn into a plus sign. And this is the result that we wanted to arrive at, because it turns out that this is there's a pattern here that we can apply systematically to any relative velocity problem. Check out these subscripts. If we'd like to know the velocity of m with respect to g, we've got three subscripts going on here. There's m for maniac, g for George, and r for roadway. So we need to insert the r between the m and the g, and we do it this way. We break it up. VMG is VMR plus VRG. See that, how there's an r here and an r here? Which is pretty reminiscent of the way fractions multiply. we're not actually dealing with fractions, of course, but if you think about it in these terms, it may help you remember the formula. The velocity of the maniac with respect to the ground is the velocity of the maniac with respect to the road times the velocity of the road with respect to the ground. The r's cancel in a sense and would leave you with m over g, which is what you want. So anytime you want to apply this equation, regardless of what your three reference frames are, here we've got George's reference frame, the roadway's reference frame, and then the maniac's reference frame. But it could be any problem in one dimension. The rule is, if you'd like to know A with respect to B, for instance, you insert the letter C twice. So A with respect to B would be A with respect to C plus C with respect to B. That's the pattern. Let's just check that this formula actually works. We'll try it with a different example. Suppose the maniac's on the other side of the road this time. So she's approaching George Carlin, and for some reason George doesn't have his eyes on the road. He's still chugging along at a kind of a sputtering 60 miles per hour to the right. She's approaching him at 80. That's why I specified that the maniac's velocity with respect to the road is negative. Sign does matter. You have to take into account whether it's plus or minus. How fast would she appear to be going as seen in George's car? So if you're in George's car, what's the apparent speed of approach of the maniac towards the car? Well, I'm hoping that this is also intuitive for most of you. If you're going forward at 60 and somebody passes you at 80, they will actually appear to be passing you from your point of view or your perspective at 80 plus 60. We would expect the relative velocity to be 140. Let's check if the equation gives us the correct result. And I put this a little too high in the slide here. Well, our general result is mg is equal to mr plus rg. Which of these numbers do we know? The one we're looking for is this. We're expecting to find that the maniac's velocity with respect to George is 140 in the negative direction. So this number should come out to be negative 140. The maniac's velocity with respect to the road, that's the negative 80. And we have to include the minus sign. And then what's the velocity of the road with respect to George? Well, George is going to the right over the road at 60. So the road is going past George in the opposite direction at 60. Hence the negative 60 miles per hour, just like before. Add those up and you do indeed get negative 140. So this equation seems to be legitimate because it works for some simple one-dimensional problems that we can easily cook up. Now, we don't really need this for our curriculum, but it's an appropriate place to stick this in, and some of you might find this fascinating and strange and maybe even upsetting and disconcerting. Here's a spaceship. And maybe it's got one of those phasers that they have in Star Trek, or, I don't know, a laser beam gun. Pew! So it shoots out dangerous laser beams at the speed of light. Now, I don't want to deal with the actual number for the speed of light because it's not convenient. If you measure the speed of light in miles per hour, it's 186,000 miles per second, actually. That's an inconvenient number. Meters per second, the speed is 3 times 10 to the 8th. Meters per second. So let's just imagine that we're measuring distance and or time in a system of units where the speed of light is a nice 1,000. That's an easy number. Now, what is m here? I think I forgot to fix the slide. Give me a second. Good. That's what that should say. Light is moving at a speed of 1,000 with respect to the ship. So this is the velocity of light as seen by somebody on the ship. So if you're on the ship, hitting the button for the phaser or the laser beam, pew, you see that light going away from you at speed 1,000. Now let's suppose that this ship is actually passing some planet, which happens to look like the moon, and you've got a space dweller living on this planet, and I'll just call him an astronaut, him or her. So A is for astronaut. The velocity of the ship with respect to the astronaut, let's suppose, is 400, which is pretty darn fast, right? That would be 40% the speed of light if the speed of light is 1,000. So here they are on the surface of their home planet watching this spaceship whiz by super fast at speed 400, and then they see the person on the ship, or whoever commands the ship, firing the phaser. Pew! So here's the velocity of the laser, I guess I should say laser with respect to the ship. It's still 1,000. So my question to you is, if the person sees the ship passing them at 400, but somebody on the ship observes light leaving the ship at speed 1,000, then how quickly is the light moving as seen by the astronaut? And if you use the same line of reasoning that you used with the maniac and George Carlin, of course you're going to conclude that the person on the surface of this planet would see the light moving at speed 1,400, because it's already going 1,000 with respect to the ship, and the ship is going 400 with respect to the planet. So you would expect to just add the numbers using this rule. The velocity of light with respect to the astronaut, so we've got three subscripts: L for light or laser, A for astronaut, S for spaceship. So insert the S between the L and the A. That's how I get the VLS SA equation right here. That would be 1,000 plus 400. Okay, seems logical, right? Well, guess what? And many of you have heard this since about 1905, since the year 1905. Oh, that's 115 years now. It's hard to believe. Scientists and the wider public perhaps have known that this is really not the way it works. Nobody thought to suggest this prior to Einstein, but as far as we know, as far as every experiment indicates, light will always go the same speed no matter what your state of motion is. So if you think back to the example with the maniac was driving at 80 miles per hour on the highway, but George Carlin could make the maniac appear to go slower by putting himself into motion at 60. So he could make the maniac look like it was moving at only 20. But what I'm suggesting to you here with this slide is that the light beam or the laser beam is still going to appear to move at 1,000 as measured, not just appear, but it will be, like it really will be going 1,000 even in the astronaut's reference frame, which is bizarre if you understand that statement. You know, if that doesn't seem bizarre to you, you probably need to think about it a little more. But there's nothing you can do to make light appear to go slower. Now, I should specify that we're talking about the speed of light in a vacuum, because light does go slower through air even. It goes significantly slower through glass, even slower through diamond. So yes, light will slow down in a medium. Sometimes it'll slow way down. But provided that we keep the discussion to vacuum, there is nothing you can do about your state of motion to make light appear to go any slower or any faster. So this just does not work. The velocity of light with respect to the astronaut is still 1,000. Even if the astronaut got a little jetpack on, or maybe he got into his own spaceship and started moving in the same direction as the laser beam at speed 999. Imagine that. Light's going this way at 1,000. You're traveling at 999 in the same direction. Wouldn't you expect the light to just barely creep past your shoulder and speed on up ahead? It's not going to be moving. You wouldn't expect it to be moving very quickly with respect to you. But even if you're going at speed 999, you would still observe the light zip right past you at speed 1,000. That example is probably even better at hammering home the point, how bizarre that is. Now, you can't go confirm that in your everyday life. That's not an easy thing to confirm. But it has been confirmed in laboratories many times over in the last 100 plus years since it was first suggested. A lot of the times it's actually confirmed indirectly, but I can tell you that the fact that your GPS works is maybe the greatest or most concrete piece of evidence that you're familiar with that this phenomenon is real. And of course, it was discovered by Einstein. These are some equations having to do with the field called special relativity, which is really not particularly challenging. It's in your book. If you take 3C, you may, depending on who you take it with, you may learn a little bit about special relativity. But there's not much calculus. I don't think there's really any calculus in it. You could have learned it in high school if you were curious. Okay, well, we need to generalize this now. The equation that I was using previously was really an equation along the x-axis. So imagine that these cars are free to move not only forward and backwards on the highway, but maybe they could move in a perpendicular direction as well. I don't mean up the page, but into that field that you see behind the cars. So there's two axes along which they can move. The velocities that we're talking about this far are actually the x components of those velocities, are they not? If you could look down on the scene here, the cars could have any velocity in that xy plane. We've really just been dealing with the x components of those velocities. So now it's time to put some vector symbols over these velocities and refer specifically to the x components. Okay? So this is the x component of the vector velocity of the maniac with respect to the ground. That velocity could have any possible direction. We're really just talking about the x component of that vector. Same for these two. Let's look at this one. The road's velocity with respect to the ground, we're talking about the x component of that vector. Okay, so the same reasoning that we use to arrive at this equation would apply just as well to any other axis, specifically the perpendicular y-axis. So let's rewrite this equation along the y-axis. Right? There's nothing special about the direction that they happen to be driving. If they were moving perpendicular to that, you could arrive at the same conclusion. How can we write these two equations simultaneously? Is there a compact way of writing both of them at once? Of course there is. It's the full vector equation. So now we're not referring to subscripts. We're actually relating the vectors. And when you see this, again, you should have that little part of your brain that wakes up and recognizes, oh, I know how to draw that. I can turn that into a picture. Because we have two vectors that sum to make another vector. How do you add vectors graphically? Well, if you place them tip to tail, you can close the triangle. This would be the vector that closes the triangle when you place these tip to tail. So, relative velocity problems in the plane can be solved with a triangle. And that's what we'll do right now, especially if it's a right triangle, because then we can use some basic trigonometry. All right, sometimes this is called addition of velocities. Your book refers to it, I think, as relative velocity. Technically, this is the Galilean addition of velocities because Galileo himself was aware of this line of thought. And it's called Galilean to distinguish it from, what would you call it, Einstein, a relativistic addition of velocities. Remember that exception with the speed of light. This equation does not work when you're talking about light. You have to use a modified formula. Okay. So here's a typical example of what you could do with this equation. Let's say somebody in a private plane needs to fly directly south this many miles to get to Albuquerque in New Mexico. Now, obviously, this is not to scale because this is the size of New Mexico. This would be a lot more than just 240 miles. And let's say that the plane is capable of pushing itself through the air at 188 miles per hour. I just Googled the speed of a Cessna. However, this plane has to contend with the fact that there's some wind. If the plane tries to just fly straight south, it's going to get blown off course by the wind. So the wind is blowing to the east. Notice I'm not saying from the east. If it was from the east, it would be going this way. To the east means from the west to the east. Here's our compass rose down here. So what is the plane's required heading? By heading, we mean which direction should you actually point the nose of the plane? Because the direction you point the plane is not necessarily the direction that the plane will actually move. So let me get out of the full screen mode here so I can mess around with... Okay. So here's my plane. I'll just click and drag. If you try to fly in this direction, but the wind is blowing to the east, can you imagine? Let me just do it over here. If you're trying to fly straight south, but the wind is blowing this way, can you imagine that what your plane would actually do is something like this? It would drift off course. You're trying to go this way, but the wind is blowing that way. So you end up just doing this. That's no good. How would you compensate for that so that the net motion of your plane really is due south? I'm sure you can figure out that if you point the nose of the plane off in this direction, so you're trying to fly this way. This is the direction that you're moving through the air. So your plane is pushing itself through the air in this direction. But while it's doing that, the air itself is moving that way. And this is a challenging concept for a lot of people the first time they think about it. The net effect of those two motions, the velocity of the plane through the air and the velocity of the air over the ground, could be that the plane just does this. So even though it's pointed at a direction west of south, it actually moves south. That's the whole idea. And this is the equation that we can use to do some math with that, to actually draw the picture accurately. Let me get my laser pointer. Okay, so I will use P for plane, A for air, and E for earth. We could have said G for ground or J for jet. Pick letters that work and it helps to label them. Did I apply the rule correctly? Um, well, the most difficult step here is figuring out how to write the equation. And truthfully, in my mind, I picture the triangle first. See, I know that the plane's going to point itself this way. It'll be moving this way through the air while the air blows to the east so that the net velocity is straight down. So by drawing the picture first and then identifying the quantities, I can then turn it into the equation. That might be the best way to proceed. And of course, after that, you should check that these subscripts obey the rule. So the velocity of the plane through the air, that's P with respect to A, but then the air goes, or the wind goes due east. That's really the air blowing over. Oh, did I? Look at that. I actually did use G for ground instead of E for earth. My bad, so just ignore that. PAG, plane is P, air is A. G is ground here. This has nothing to do with George Carlin. George is gone in this problem. Okay, so this is the wind over the, well, it's the air over the ground, which is what we call wind. And here's the plane going with respect to the ground in the desired southward direction. Okay, so the triangle checks out, right, with your intuition about relative motion. And notice how VPA is tip to tail with VAG, and that VPG is in fact the resultant. So the picture is drawn correctly, and notice that the subscripts do obey the appropriate rule. I've inserted two A's between the P and the G. Okay? So now let's label this angle. I could have called it theta. For some reason I like the letter phi. And what do we know here? Remember, we know that the plane is moving at a speed of 188 through the air. That's this speed right here. It's the plane pushing itself through the air. The wind is blowing at 40 miles an hour. So in terms of this angle, we know the opposite side and we know the hypotenuse. And why am I even doing this? Well, if you recall, the question was asking what should be the heading of the plane. Which direction do you point the nose of the plane? That is what phi will tell us. Whatever phi is, that's the angle from south that we point the plane. Okay, opposite side and hypotenuse, we should be using the sine function. So I will take the inverse sine, also known as the arc sine, of the opposite side over the hypotenuse. And those numbers, again, please ignore the E for earth. Those numbers are 40 over 188. That's the ratio for which I'm computing the arc sine. You can check that in your calculator. Make sure you're in degree mode. 12.3. Okay, so it's not going to be good enough to point the plane south. You will blow off course. You have to tilt the plane and make the heading 12.3 degrees west of south. West of south, because imagine facing south, you would have to turn towards the west to reach that direction. So that's a good way to express the answer. Now that's not the only thing we can determine having drawn this triangle. Do you notice how the hypotenuse is longer than the adjacent side? The length of this velocity vector represents the speed of the plane through the air, which we know to be 188. What if we'd like to know how quickly the plane is moving with respect to the ground? That might be the more important speed. So if we could somehow determine the length of this adjacent side, that would tell us how fast we're actually moving over Earth, and we could use that to determine the length of time it will take to reach Albuquerque, which is something we might want to know, right? So how do we do that? If we know the hypotenuse, we know the opposite side, and we know this angle, what's the quickest way to get there? Remember that rule? If you take the hypotenuse and you multiply by the cosine of an angle, that will give you the length of the adjacent side, which is what we want. So the velocity of the plane over the ground would be VPA, that's the plane through the air, times the cosine of that angle. We already know those numbers, so 188 cos 12.3, and we are in fact going a little bit slower. That's kind of interesting, right? Even though the plane is capable of moving through the air at 188, in some sense the speed gets subtracted because of the wind. Okay, now that we know the speed, remember for constant speed you could say distance equals velocity times time, or speed times time. Solve that for time, you get time equals distance over velocity. So divide the speed over the ground into the distance that we have to travel, see how the units work out, and we find that it will take 1.3 hours. If there were no wind, the plane could actually fly due south at 188 and get there in less time. But because of the wind, some of your speed is subtracted, so to speak. That's an imprecise statement. Obviously, you want to use the equation and the picture to do things precisely.